Okay, let's have a look then at our new homologous series, and their general name is the alcohols. In the unit reference sheet, it does refer to primary alcohols. There are also secondary and tertiary alcohols. I will explain what those are because you might see that described somewhere. But we're really only considering the primary alcohols for now. The general formula for our primary alcohols is CN H2N, let me get this right in my head, plus 1 or 2 plus 1. And then the functional group is OH. All right, CnH2n plus 1 OH. So we're going to go through a series and work out the names and the formulae and all that. So if we start with number of carbons formula and name, that should make it work. So if we've got 1 carbon, what's the formula of our alcohol? It is C1, but we never put a 1, do we? So it's just C on its own. So yeah, absolutely right. CH3OH. Now, what's the starting part of the name if it's only got 1 carbon? Meth, yeah. So it's methanol. Meths. All right, so this one's methanol. Now, I could probably now just leave you to do, up to 10. You could do it, couldn't you? Because you've now, yes, you could, because you've got the general formula, and the pattern of naming is exactly the same. So let's just do some obvious. So 2 carbons, the formula will be C2H, yeah, C2H5. Whoops, what happened to my H there? I think the board's slightly, there's quite a lot out. Just let me try that one again. H5OH. So that one is ethanol, yes. And that's the one that we're most familiar with, and it's coming up to ethanol season, of course. So, yeah, over the next month or so, I suspect there'll be some encounters with ethanol. Hopefully not the methanol, because that, what, methanol is poison. Do you know what it does particularly? It causes blindness. And if you're desperate, then, well, yeah. But they actually use ethanol to treat methanol poisoning. So if somebody on the streets, for example, has been drinking meths because they're desperate, then you can actually treat that with ethanol. So assume there's a sort of competition in the body for it. But yes, I think there's a huge amount of damage potentially there. Right, let's just do a few more. Let's, I don't know, take it down to 5 perhaps. So 3 carbons would go C3H7. You keep losing one. And we shall call that one? We shall call that propanol. 4 would be C4H9OH. And we shall call that one butanol. And then C5 would go C5H11 would give us pentanol. And we could keep going forever, pretty much. Well, I don't think we can. But your assignment is going to get you to explore some of the properties of these, but going a bit further than this, up to decanol. And the important thing is this OH group. The OH group makes a huge difference because the nature of the bond in the OH group is that it is polar, isn't it? Think of water. you've got the two OH bonds, is incredibly polar. So having an OH group on an alcohol gives it a polar end, if you like. Now, in a small alcohol like methanol or ethanol or even propanol probably, that polar end to the molecule is very, very significant. But the longer the hydrocarbon chain gets, the less that OH group is actually going to have any influence. So there will be an impact on things like how soluble these are in water, how well they mix with water, sometimes described as miscibility, and on things like their boiling and melting points as well. So, you know, you do find that it's not just the length of the hydrocarbon chain, it is also the OH group that's important. So bear that one in mind. All right, I'm not going to scare you with a new assignment this week, but it's coming. Okay, so if that's our start of our basic series, we're not really defining anything about the structure of these. So I just want to give you the distinction between primary, secondary and tertiary alcohols. I'm going to do this off the top of my head rather than try and find my folder, so fingers crossed, we'll see what happens. The primary alcohols, which are the ones you want, are... hang on, I'm just going to reset the board. I'll put this on pause while I do it. Okay, the board should now be lined up properly. So, let's try that again. Yes. Okay. Oops. Can't get rid of it. There we are. Okay, primary alcohols are like these appear to be, where you'd have a chain of carbons and you have a situation where the OH group is attached to a carbon that is otherwise only attached to, oh, I've forgotten the definition now. All right, now I've got to try and get the difference here. And it depends whereabouts in the chain the OH group is attached. If I make a mess of this, I shall have to fish my folder out and try and do it from there. And actually, that might not be a bad idea anyway to save in making a mistake, so just bear with me. But it's whereabouts or what else is attached to the carbon that's got the OH group on it. And I'm sure I've got this written down, but I've lost it. Nope. Oh, there it is. Got it. A secondary alcohol would be if you've actually, your carbon with the OH on it was joined to two other carbons. And they can be joined to anything you like, hydrogens or other carbons. I need to introduce a way of describing these groups in a minute. And then a tertiary alcohol would be where our OH carbon is actually attached to three other carbons, like that. And then what's joined onto them doesn't really matter. All right, now when we start modelling isomers of these, then you'll actually find you will model primary, secondary and tertiary ones, but the assignment only focuses on the primary ones. Now, these groups that are attached are known in a particular way. They're called R groups. So let's start at the top. This, for example, a carbon and hydrogen combination there is an R group. So here, right, you have two R groups. Right, so we're really talking about little hydrocarbon groups, but they're just known as R groups. There's another way of describing them as well, but I'm not going to go down that alley at the moment. So here we've got 3 R groups, and that is attached to the carbon that's holding the functional group, the OH group. So that's the difference between primary, secondary and tertiary alcohols, in case you come across that. But like I say, the assignment only really focuses on the primary ones, so I'm not asking you to draw lots of different ones at that point, but we'll do that now. Right, let's have a look at some isomers in the alcohols, because obviously not only can you rearrange the carbons like this, so you can have branched chains, you can also put the OH group in lots of different places. It doesn't have to just stick off the end of a molecule. So let's have a look at isomers and their names. Now I'm going to set you off on this, and you can either just draw these or you could try modelling some of them as well. Modelling sometimes helps, largely because you get a 3-dimensional idea of how they work. Just drawing them on paper, it's sometimes a bit hard to see if you've done the same thing more than once. And what I'm going to ask you to do is to see how many isomers of, just try to decide which one to do, pentanol, I think. There are about 8, so I'm not expecting you to get all of them. And you can just sketch them down on paper just using the carbons if you want, and an OH group stuck somewhere. But the isomers, I'm going to give you 1 or 2 examples here. Let's have, I'm not going to do the pentanol one, let's have this one. 1, 2, 3, 4, and then let's stick an OH group on the end there. I'm not going to put the hydrogens in, we'll assume they're like that. What's our obvious name for that? Butanol, yeah? So that's butanol. However, it's actually butan-1-ol. You will see these sometimes written 1-butanol, but I think the correct way is butan-1-ol. So the ol is telling you where the OH group is, yeah? And we start numbering from this end because it's nearest our functional group, okay? So in that case, that would be, it is butan-2-ol. Right, can we have butan-3-ol? No, because it's the same as? Yes, 2. All right. Now, you've got other options that you could put branches in. So we could have, I think I can do it with this one. 1, 2, 3. If I put a branch there and an OH there. Ooh, what should we call this one? Is that still butanol? No, because our longest chain is 3, so it's going to be based on propanol. Yeah, methane, ethane, propane. All right, propanol is our stem, if you like. Doesn't matter which end we count from. Any offers for a name on that? Well, methyl. Yeah, it's a single. Yeah, the OH is only ever named on the end of the molecule. Because it's an alcohol, it'll always be something ol on the end, so that's fine. So it will be a 2-ol, and so the other bit that you got was 2. That's it. 2-methyl. That's that bit. Doesn't matter we go 1, 2, 3 or 1, 2, 3. Yeah, propan, 2-ol. Well done between you. So 2-methyl propan 2-ol. All right, and again, it's just following those rules, isn't it? And they're not mysterious once you make sure you don't just make it up, which is always something people have a tendency to do, is just sort of have a stab at it, but use the rules and you're there. You could have great big long example with other branches on it as well, and actually as our starter exercise for the later session, I'm going to give out some cards between you with different names on, that you can either draw them, you can draw them on the little whiteboards, you can model them if you want to, just for you to sort of check with each other that you can get the hang of these things. But that's converting from a name into a structure. All right. Okay, that's some of, I'm not sure if that's all of, it might be all of the isomers of butanol. I can't think of any others, because I think if you move this OH group around onto any of the other carbons, you've got the same thing, haven't you? Doesn't matter where you put it, you'll end up with the same thing. So I think you've only got those 3 isomers. All right, so have a go now, either on paper, on the mini whiteboards, with the models, whatever you like. How many, well, there are, as I say, about, I think there's 8 altogether, may be wrong, but isomers of pentanol. And I'll give you a start. So you would go pentanol, 1, 2, 3, 4, 5, okay? And it doesn't matter, I've started curiously, like that. And that one would be pentan 1-ol, Now, that means I'm numbering from the right-hand end. It would be exactly the same if it was at the other end. So that's pentan 1-ol. So you should be able to get a couple more without too many troubles, and then you will find that there are some slightly trickier ones that you can chase down. All right, so that's 5 carbons, so the pent bit. It's saturated, there are no double bonds, so it's pentan. You could have an unsaturated one with a double bond in it and call it pentene, or penten 1-ol. Then we'd have to say where the double bond was, so we're not going down that route. So pentan 1-ol is a saturated hydrocarbon chain of 5, and then the ol, the OH group, is attached to carbon 1, so pentan 1-ol is your starting point. Okay, so I'm going to give you a few minutes, give you 5 minutes or so to have a go. Well, it might take more than 5 minutes. Have a look at each other's as well, share them, because you will probably find, most people find that they do the same one twice, just, putting it in a different order, or, sorry, not a different order, that would change it, but back to front perhaps, or from the other side, or upside down. Bear in mind, you can look at these from the other side, you can flip them left to right, and they retain the same name. All right, so I'll turn this off while you have a go at that. Okay, what's the second one that you would obviously go for? 2-ol, yeah. So we'd go 1, 2, 3, 4, 5, and we would stick our OH there, fill everything else up with hydrogen. So pentan 2-ol for that one. And the next most obvious one would be 3-ol. Yeah, I think I missed something there, didn't I? So yeah, we can have 3-ol as well. So we can go 1, 2, 3, 4, 5. Stick it on there. But after that, things get a little bit more interesting, don't they? Right. Anybody want to offer me a name of another one? Okay. Right, okay. I'm not 100% sure on that one. Hang on, let me go back to my list. I think you might find, actually, it's possibly gone round a corner, but we'll... No, that is right, actually. It's on my list. Right, that's the one I usually have at the end. That's why I was thinking about that one. Right, so it was propan 1-ol was your stem. So there's your stem, propan 1-ol. And then your 2,2-dimethyl would give you those, yeah? Excellent, that'll do nicely. So that one is 2,2-dimethyl propan 1-ol. Woohoo! Yeah, my drawing could be better. Okay, that's one off the list. Any others, please? Yeah, I mean that's. Sorry? Yep, that'll do nicely. 2-methyl-butane 1-ol. So butane 1-ol would be the 1, 2, 3, 4. There we go. And then 2-methyl would give us that. Okay, there's another one related to that. Okay, give me a name. I think that's the one we just got. But if you move the OH on one, you could have. Yeah, well it is. Ah, dear, my hydrogens are very messy, aren't they? Look. You could have 2-methyl-butane 2-ol, couldn't you? So I need more space. 2-methyl butane 2-ol. I'm going to leave the hydrogens out of it because it's just getting too messy the way I draw. Okay, there was possibly 3 more. I'm just checking my. Yeah, I'm not sure. 1, 2, 3, 4, 5, 6, 7, 8. I've got 9 options, but that means that 2 of them are the same, and I've not spotted it. Right, you could move your methyl group on one. How about those 4? How about putting that there and that there? What could we call that one? It's not 2-methyl because we start numbering from this end. So it's 1, 2, 3-methyl. Then it's butane. Yeah, you start numbering from the end that's nearest a functional group, preferably. If you haven't got a functional group, then it's a branch. So we would start, preferably, at the end nearest the OH. So we're going 1. Oh, that's supposed to be a 1, 2, 3, 4, like that, because that's nearest that. So what did we get? 3-methyl. Butane 2-ol, yes, that's it. Got there in the end. Oops. Now we can't have 3-methyl butane 3-ol, can we? Because they would actually then both be on carbon 2, like the one up here. But we could we swap those round and get anything different? No, we couldn't, could we? Just I think. I'm sure there's another one. Any offers for another one? Okay, give me a name. Oh, I wasn't even thinking about cyclic ones, but you could theoretically have a cyclic one, yeah. But rather, yeah, cyclopentanol in some form you could have, and then there'd be branched options possibly for that. So, yeah, I think we'll leave the cyclic option. I think there's another straight one. Well, no, because if you've got OH on 1 and the C on the 4, you've just got pentane 1-ol, haven't you? Because you've actually got a chain of 5.
Could put the OH on C that's branching off from 3.
But then it wouldn't be branching off because it would actually be on the end. If it, you tend to think of this as a branch, but then your longest chain would actually be around that corner. So yeah, it does take a while, and I think I may have missed one there, but you're getting the hang of that. So I'm not too concerned about chasing those down, because I'm going to give you some more examples later to play with anyway. What I want to get on to quickly, and it will only take sort of 10-15 minutes probably, but sort of like to be done with it by past. And then I'll spend 5 minutes telling you what we're doing after break. But we've got a little bit of practical work to do. And you've got in your files an instruction sheet which it may just say properties of alcohols. It may say properties of ethanoic acid on the other side. It shouldn't do. But properties of alcohols, they're just a few little practicals to do. And it says 30 minutes on the back. It shouldn't take 30 minutes, but I'll turn this off and give you the instructions. I know. Can't do much about that. Yes, there is a gap in the recording. Never mind. There are out there a whole lot of free bits of software for drawing complicated molecules, because getting the angles right, getting the length of the lines right, getting single bonds, double bonds, it is a pain. But you do have to sort of learn how to use these pieces of software. That they're not totally intuitive, but all you have to do, I haven't got one installed on this computer at the moment, because what happens over the summer is that they sort of rebuild the computers, and all the neat little bits of software I put on there, of course, over the year disappear. And I will probably put one on if I'm allowed to, you never know. But if you literally just search for free molecular drawing software, you'll get quite a lot coming up. Now, these are usually fairly reliable and fairly safe. I say fairly, they are, because they are, they're not the sort of software that's going to be hijacked, particularly for evil purposes. But one particular good one is this one, and it comes up sort of fairly early on your search if you put in that free molecular drawing software. You get this one, ChemSketch freeware. And ACD Labs are, quite a reliable source. That's what I opened up this morning. But of course, you can have a look around. You can actually sort of try several and see what works. But doesn't want to know this morning. It will give you options to buy expensive versions of it, which obviously, if you were working, let's say, at postgraduate level and you needed a whole lot of very complex molecules for a research paper or something, you might do that. But there's always a neat little freebie, basic version, and that's all you need. And you have a selection of bonds Usually the skeleton formula stuff is there. You get sort of hexagons and pentagons and single lines and double lines, and you can then place the letters to represent your atoms in there. So yeah, that is a rubbish demonstration, but I will get it up and running, and I will show you before you have to get into that with the assignment. So yeah, don't panic that it's not coming out for a while yet, but you know, you don't need to be worrying about actually drawing stuff by hand for that, or trying to make Word do it. Now, you might have other drawing software that you can use. I mean, I don't know, Frankie, you might use stuff that would do it. Yeah, I mean, if you are familiar with drawing software, then you might have a way of doing it without using a specific program. I had a student a couple of years ago now whose husband, I think, was an engineer or something like that. So he had some design software. I think it was a program called Bluebeam, and she used that, and it actually produced some really, really clear, well-structured molecule shapes. So there's plenty out there, but don't feel you've got to try and do them yourself. Okay, now we lost a little bit before break in terms of reactions, and so I'm just going to pick up on some of those and recap one of them at least. And it really came under the section of properties of alcohols. Now, I talked about a few of them as we went through, but the chemical bit we didn't really get round to. You did the practical, so I'm just going to pick up, because I've got ahead of myself here, I'm going to pick up on a bit that you were looking at in the practical work anyway. So, properties and reactions. Yeah, all right. If we start off with some of the physical properties, we have the same effect of increasing length of carbon chain as we had with the alkanes. So if we look, for example, at, let's say, boiling point and melting point, what do you think will happen to those values as the carbon chain gets longer? Those temperatures might rise, yeah. Reason being, of course, you've got the interactions that we talked about before. You've got the interactions between the hydrocarbon chains. You've also, of course, with the alcohols, got the OH groups to think about as well. So you've got, we can make this quite simple because it's like the alkanes, so we've done it before. So we've got increasing boiling point, all right, and melting point. Get used to using abbreviations. All right, you might get back to this and think, what? That's increasing boiling point and melting point as carbon chain increases in length. All right, we're not going to go into a full description because we've already done it. Yeah, so we've done that with the alkanes. Also, in terms of things like density, what will happen as the carbon chain length increases? That will increase as well, yeah. So we've got increasing density, bigger molecules, heavier. So as the chain increases, I'm not going to put the whole lot in. What else can we put in? We were talking this morning about the solubility of alcohols. So, yeah, right. What happens to the solubility as the chain length increases? It decreases, that's right, yeah, it goes down because we've got that increasing hydrocarbon chain, which overcomes the, that's it, OH group, yeah. So, decreasing solubility with increasing chain length. I'm not putting the full explanation in there because that is part of your assignment. So, right, you will need to find the full explanations for that And I'd expect you to be talking about things like hydrogen bonds and then the other intermolecular forces that will actually hold the longer chains together more. And that whole thing. All right. If we look at the reactions, you didn't really. What did you do this morning? You oxidised. Oh, this is a good sidetrack. You oxidised some alcohol. That was the reaction that produced the smelly stuff. Did any of you detect the smell at your benches, or wasn't it until we stuck it all down the sink? You did actually, yeah. And it was a bit like sort of slightly off fruit sort of smell. Yeah, that sort of. It wasn't fruity exactly, but as though it sort of slightly off fruit. It had produced what we call an aldehyde, and you can oxidise. Right, that's the reactions I'll just do a couple of reactions. We don't need too many of them. But you've got oxidation to aldehydes. Now, we aren't doing the aldehydes as a group, but there's a relevance here in that this is a chemical reaction you can do in a tube that your liver does in its cells. All right? So I'm going to use this as a sort of comparison and try and give us a bit of a sort of crossover between the chemistry and the biology. You start off with, what was the alcohol you were using this morning? Ethanol, yeah. And the mixture of sulfuric acid and potassium dichromate oxidised the ethanol. All right. Now the reaction, and I'm only going to do it in words because we don't need to do the actual formulae, and I don't trust myself to get it completely right. But if you start, hang on, it'd be far better if I wrote ethanol, wouldn't it? You can convert it into an aldehyde called ethanal. Now, the problem with ethanal in the body is that if we're trying to process ethanol's toxic, ethanol's even more toxic. And it is possible to actually take it further than that. And if you keep oxidising it, you end up with something else. And it's a group that we haven't met yet, and that's the acids, the carboxylic acids. And if you keep going, so I'll put it in as a dashed arrow because this would be a possibility, you can take it to ethanoic acid. Now, that's a step beyond where we are at the moment. Any offers for what we might know ethanoic acid as? It has a more common name. Beginning with A? No. Think of a common everyday acid that you use in your kitchen. What are acidic things in your kitchen? Just give me an example. Sorry, did somebody say vinegar? Possibly not. You should have. What's the acid that you think of in vinegar? Ah, come on. You've got all quiet on me. Acetic acid, you heard of that? Yes, no, maybe. All right, name me another food acid. Thank you. They are out there somewhere. Acetic acid is the one that's in vinegar, and that's acetic acid. All right, chemists call it ethanoic acid. Biologists probably call it acetic acid. And this is, it's a long-running feud, I suppose. I'm caught between the two. Sorry?
Can you drink too much vinegar?
Yes. Yeah, definitely. You drink vinegar? But yeah, it wouldn't do you a lot of good. Because it's the same. I mean, for one thing, it would damage your teeth, wouldn't it? Like drinking a lot of fruit juice with the citric acid in. Anything acidic is going to have a sort of slightly corrosive effect. They are very weak acids, all right, not dilute, but weak. They don't produce a lot of hydrogen ions. But ethanoic acid is, it is essentially acetic acid, and its up-to-date name is ethanoic. So you could have kept going, and if you had, you might have started to smell a slightly vinegary smell, all right? We didn't keep it going that long. In your body, this happens when your liver processes ethanol. All right, but what we have to do that, instead of, obviously your liver doesn't get some sulfuric acid and some potassium dichromate and boil it up, does it? But we have enzymes. Now, we haven't met enzymes yet, but I'm sure most of you have heard of enzymes, haven't you? Yes. And enzymes speed up chemical reactions that wouldn't otherwise happen fast enough to keep us alive. We have one enzyme that works here, just basically called alcohol dehydrogenase, and dehydrogenase tells you exactly what it does. It takes hydrogen off the ethanol, and that is a form of oxidation. I know that's, you know, not an area we've got into, but we can convert ethanol to ethanal by taking away hydrogen. Now the problem with ethanal is nasty stuff. I mean, you could tell from the smell that you got this morning, that's not very nice. And it's really quite toxic in the body. So we then have another enzyme called aldehyde dehydrogenase that will do that. And then our bodies can process this quite easily. You can use that for energy, you can convert it into much less toxic substances. So we have two enzymes. Now, there are certain people who don't have the second one. And therefore, if they drink alcohol, can only get the reaction you did this morning from ethanol to ethanal. Now, do you know which part of the world is a bit prone to having problems processing alcohol? That's it. I thought the Australians drank no end. Oh, do it? Aboriginals, yeah? Ah, right, okay. They are probably lacking that then. But there is another group, particularly, yes, East Asian, so Japanese particularly, don't have that enzyme. And they get what's called Japanese flush. And it's like they just sort of go really red, the blood rushes to the face, they feel really sick, and it can actually be quite a dangerous thing. But it's also a way, oh, I'm sidetracking goodness knows where now. It's also a way of treating alcoholism. Because if you block the enzyme that does that, then when somebody drinks, they'll produce this and it will make them feel phenomenally ill. All right, and it's a drug called antabuse, or disulfiram is the name of the actual chemical. But if you can stop the conversion of this to this, then whenever somebody drinks, they'll get a build-up of this and can feel really, really unwell, end up hospitalised. So, yeah, anyway, that all you did was that first little bit in a test tube. But we'll be back to some of this. You know, it's got relevance further on, not least when we're doing enzymes, I suppose. So that's one thing. The other thing, which leads me on to our other bit, is good old combustion. Now, you remember combustion as one of the reaction types that we did when we did the practical circus? And there's a definition of combustion where you start with a carbon compound plus oxygen gives two things, water and, yeah, carbon dioxide, yeah. So general equation for combustion is something plus oxygen gives carbon dioxide and water. And that's what you did in the little dish. And if you put flaming brandy over your Christmas pudding, that's what's happening there. But we're going to demonstrate this in a slightly more impressive way in a minute. So if we were to take, it doesn't matter which of the alcohols we take, just going to give you let's take the ethanol one. So C2H5OH. I'm going to get you to balance this. Okay, do me some balancing. What should we stick where? What's your first thought? We need more hydrogen, yes, but that wouldn't be my first thought. Carbons would be, yeah. You read from left to right, wouldn't you? No, it doesn't matter particularly. Any offers for what we can put where? Yeah, 2 in front of CO2 for a start. What have we got now? I'm just going to keep following your instructions and see what happens. H2O as we go?
Yeah, it's got so. I'll do quick one. 3.
All right, we'll stick that there. How are we doing? Are we there? 2 carbons, 2 carbons. How many hydrogens over here? 6. How many over here? 6, that's all right. How many oxygens? 2 there and 1 is 5. 2 there, sorry, 4 there and no, 3 is 7. So we need more oxygen on that side. What should we do? Yeah, if we change that for a 3, yeah, are we all right now? Carbons were fine, hydrogens were okay, and we've now got 3 2s of 6 and an odd 1. We've got 2 2s of 4 and 3, 7 on each side. Yeah. That's not the only thing we get out in combustion. What else do we get out? When you burn something, what do you get? Nyeh. Wasn't what I wanted. Heat, yeah. Energy. That's where we're heading. Our next step after this bit is to take a bit of a sidetrack into some basic energetics. So we're going to think about the energy that's released when things combust to start with. Then we're going to look at energy exchanges in different sorts of reactions. So we ought not to forget energy. Okay, now next thing we're going to do then is to move on to a demonstration. So just bear with me because I need to turn this off. I think I'll put it on pause for now. So this is one of the reactions that we've just looked at. So you've got the ethanol, is that one? I suppose we ought to just stick the other one in as well, oughtn't we? Seeing as you've seen them both. So formula for propanol, doesn't matter which one because that's not going to be evident from this. Formula? Yes? Yeah, C3H7. OH, yeah. Alright, and the rest of it's the same. Right, and some balancing in that one. Where would we start? Let's take the same approach as before. Start with the carbons, so, right, 3 in front of the CO2. How are we doing for other stuff? We'd better sort out the hydrogens, so how many hydrogens here? 8, so we want 4 over there. Right, now we can sort the oxygens out, all right? I think, you know, what you did before was to dive into the oxygens perhaps a little bit too soon. So how many oxygens on the right? 3 2s are 6 plus 4 is 10. Oh, is it? It is, isn't it? Okay, how could we get round that in a sneaky sort of way? We can. That's one option, is to double it all the way through. You do actually have another option. How could you make 10 on this side? No, you don't need to bracket anything, but you could use a half somewhere. On the O2, yeah, what? Well, it's, yeah, the thing is it's not. What you've got to remember is these numbers don't just represent molecules, they represent moles, don't they? Large quantities. So, what number would we have here? If you're allowed to have halves? 4.5, yes, 4.5. We always use fractions rather than decimals, but you could have that. Now, if you don't like that, yes, you can double it all the way through. So we could alternatively achieve the same balance, couldn't we, by going 2, let's do them underneath, then 9, then, yeah, you can do it, you can do it. All right, so you've got to remember, it's about ratios. That's what, you know, this balancing equations, or what we call stoichiometry, is about having the same amount going in as you've got coming out, or vice versa, and importantly, you know, just making sure that the two sides have got the same. And it doesn't matter if you have a half, you can't use any other fractions, right? So we're not having thirds or quarters or fifths or anything like that, but you can have a half. And it is something that we will start using at some point. It just was in my mind that, you know, I thought we might meet it in here. And you then have the option of either leaving it in a 1 to 4.5 ratio or making it all up to whole numbers. But like algebra, you know, you must do the same thing to both sides. So if you double the left, you double the right, all the way through. And then, you know, if you do go through and balance that out, it'll all, you know, it'll all be there. Okay, so this energy then, I've detailed, I didn't put it on here, but the energy that comes out, it's in the form, well, with the whoosh bottles, what sorts of energy had we got? We've got thermal, the heat, what else have we got? Sorry? Well, yeah, but as an energy, kinetic energy probably, yeah? Forcing the gas out. Have we got any others? Could you, light and sound, you could hear it, couldn't you? So there's a lot of different forms of energy coming out of that. And where's it all come from? Well, she rightly said, it's to do with making and breaking bonds. So we're going to use this just to start thinking about the energetic side of things. And next week we'll do a lot more on that. So this is, yeah, it's quite, this is, I'm going to put introduction because this is not taking us very far. All right, so energetics. And in this unit, you do only get the introductory bit because if you've looked ahead, you know what the title of the second chemistry unit is. Energetics, kinetics and redox. So in the second unit we do a lot more exploration of energy changes in chemical reactions, and you do a lot of complicated calculations and graphs and all sorts, working out some good A-level stuff actually. What we need here is just an overview really of what's going on in a chemical reaction. Now, if I was to give you or get you to make up the bead models for ethanol and oxygen, what would you have to do to take those same models and convert them into carbon dioxide and water? Yes, the first thing you'd have to do is break the bonds, take them apart, take the beads off their, oh, I had an ethanol in here, so, oh, there he is. So, yeah, you'd start off by going, oh, we'd get, oh, pop, pop, wouldn't we? So you'd have to break the bonds first. And that's what happens in a chemical reaction. The first thing that has to be done is the individual atoms, if you like, have to be released from their starting point. So there's breaking of bonds. But then once we've got them all loose, how would you then get them into their new compounds, their products? So it would have to form new bonds, yeah. So it's about breaking bonds and making new bonds, isn't it? So the bonds have to be broken in the reactants, and then the bonds will form in the products. So let's start with that. These are just sort of a few key thoughts that we're going to need to use as we go through the whole section on energetics. So bonds break. I need to put something else in with this in a minute. So I'm going to leave a bit of a gap because I want to add something to this. So bonds break in the reactants, and then bonds form in products. All right, now, which of these requires you to put energy into it? Breaking them, yes. So, you know, that takes a bit of effort. I'm probably overdoing it there, you know, the dramatic version. And just pushing them back together again, well, it's not obvious, but that releases energy. But the bonds breaking in the reactants, therefore, requiring input of energy. So the bonds forming in the products actually releases energy. Now, I'm going to need two words off you in a minute. Okay, now the first one, where you're putting energy in, there is a word that describes that. The energy going in. Think of two bits of words, one that means in and one that means heat. Yeah, endothermic. Yeah, does that make sense? This is an endothermic process. All right, so this one puts energy in. Now, what effect does that have on the surroundings? Temperature-wise, what would that... No, it doesn't, does it? Think about it. You've had to take energy from the environment and put it into that. So it actually cools the environment, an endothermic process. We're going to look at the balance in a minute. So this is endothermic, this process. And, you know, you don't just get one of these occurring, you get both. So the other, I should be able to get a chorus on this one, will be? Thank you. Ooh. Now, exo then means outside, yeah. And so this one is giving heat out. Now, remember, you can't create or destroy energy. There's only a finite amount of it, but you can convert it from one form to another. Right? First law of thermodynamics or second law? Doesn't matter at the moment, but you can't create it or destroy it. You can convert it. So this means there must be a balance going on here. You know, you can only have so much energy involved in this. But an endothermic and exothermic reaction have different impacts on the environment and, of course, on the chemicals. So I'm just going to compare the two and see if this works. All right, drawing up a little table here. So we'll have endothermic, exothermic. And I know I could use the table tool up there. Effect on, let's just say chemicals, which is a bit simplistic, but that'll do the job. And then effect on the environment. And I want to introduce this now because it's one of the biggest mistakes that people are prone to making. Right. An endothermic reaction, we've put heat or energy in, so their energy level will... No, yeah, it's been a long morning. So their energy level will increase, yeah? And where is that energy coming from? Outside, yeah. So energy level or content is increased. So once you've pulled the reactants apart, they've got more energy. An exothermic reaction, on the other hand, causes the chemicals to... Well, yeah, I've not phrased that very well, have I? Energy level of the chemicals will decrease, yeah. So where has that energy gone? Not yet, no, not necessarily. It could just influence the environment. I'm just generally doing endo and exothermic at the moment. So the effect of an endothermic reaction on the environment, Cooling is a good one, yeah. So, let's just put that. Lower energy. And a good example, this is why I want to put this in here, is that it has a cooling effect. Because that's something you're going to measure next time. You're going to do a whole bunch of chemical reactions, some of which are overall endo or exothermic. And so you'll be measuring temperature changes. So this is just to set the scene for where we're moving on to. And so, surprise, surprise, what happens to the environment with the exothermic in terms of energy? It heats it up, yeah. Now, that's for, we were just talking about breaking bonds, making bonds, but if you have a whole chemical reaction like combustion, you've done both of these, haven't you? Yeah, so we broke the bonds in the ethanol and then made some more bonds in carbon dioxide and water. So we did an endothermic reaction to start with and then an exothermic reaction afterwards. One of those involved more energy than the other, didn't it? Which one involved the most energy exchange? The exothermic, yes, because it gave off quite a lot of heat and light and sound and other stuff. All right, so a chemical reaction is going to be both of these, but usually one will be bigger than the other. So you can have completely endothermic reactions that cause cooling overall, or exothermic reactions that will cause heating. So overall, not surprisingly, we describe combustion as an exothermic reaction, don't we? Yeah. It doesn't have to be heat, but more often than not in chemistry it is. So, you know, we tend to use the word, well, part word, thermic. If we were just talking energy in the broadest sense, that's a bit of a long shot. Did you think of a word that means energy in and energy out, rather than thermic? Yeah, I wasn't sure. You might have heard it if I mention it. Endergonic and exergonic. The erg bit really is about energy generally, rather than just meaning heat. But, you know, as far as chemistry is concerned, there's usually some heat involved. So endothermic, exothermic is fine. So what we have is, in a reaction, we've got usually an imbalance. So energy, I think I'm just going to take it to this point. Energy changes in an overall reaction reflect balance between endo and exothermic. If we wanted to express this, what we're going to be talking about is an idea called enthalpy. Now, that's got a very similar name to another word in chemistry, which is entropy, which is not the same. Entropy is a measure of disorder, if you like. And so, for example, a gas has more entropy than a liquid, which has more entropy than a solid. So that's something that's not, you know, relevant here necessarily. But we're looking at enthalpy. And what we're going to be using, there are all sorts of different types of enthalpy. They have different definitions. And what we're going to look at are bond enthalpies. And these are stated values. There are standard values of these, so that we know what the bond enthalpy is of a carbon-to-carbon single bond. We can look it up in a book. We know what the bond enthalpy is of a carbon to hydrogen bond. We know what the enthalpy is of a carbon to oxygen bond, and so on. And we can look up all these bond enthalpies, and we can work out how much energy there is in there that can potentially be released when we break it down. And then when we form the new bonds, we can again look up the amount of bond enthalpy in the carbon dioxide bonds and in the water bonds, and work out how much is released when they form. And so we'll then be able to look at a balance to say, well, you need to put this much in to break the bonds apart, but you get this much out when you form the new bonds, and consequently the balance between these two is such that, oh well, surprise surprise, if it's this particular molecule, then your overall reaction turns out to be exothermic. All right, so that's where we're going with that one. It's not, so I'm not going any further into that for now, but for next Monday we will I think next Monday we will have to use the morning up, I think, to catch up with the biology I'm going to miss tomorrow afternoon. All right, just a few reminders and things now. This afternoon you are on self-directed study. If you want to stay in here, you can do. If you want to find a computer, you can do. As far as I'm aware, I'm out from 1 till 2, observing the guy who didn't come in to see us this morning. So that's going to mess things up, isn't it? But yeah, it's not my problem. So you have several things to make sure you're getting on with. First of all, the osmosis assignment needs to be in here by, well, I said 4 o'clock, but I may be going before that if, yeah, it depends how the afternoon turns out. I'd aim to get it in by 3 if I were you. You've got UCAS to be getting on with, the What's in the News forum to be getting on with. What else have I got that you can do? I've got a list here. Finish the Cells 2 assignment, get on with UCAS applications, post a topic or a comment on the forum, and what you could be doing if you're wanting to get ahead on the biology, if you haven't done it already, is listen to the blood glucose podcast. I wouldn't listen to the blood pressure one yet because that's a bit over the top. We haven't talked about that, but the blood glucose one. Or you might want to listen to them both because they're only 10 minutes each anyway. So they're not difficult. It's just me basically talking for everything that needs to be in the assignment. Everything needs to be developed in the assignment, shall we say. Tomorrow you've got Roy in the morning, and then you've got Maria in here in the afternoon. All right, catching up with the session she missed the other week when she hurt her ankle. So I've lost a biology session with you this week. So I'm going to stick that on to next Monday. So next Monday we'll spend in here. I think I might do all morning on chemistry and then do biology in the afternoon, and then I'll have caught up. All right, so that that will settle my mind. Not sure exactly how long it will take to catch up, but that should be okay. All right, so we'll wind up at that point, and the rest of the day is yours to use productively.